So, for example, let's say we had a potentiometer, and it was a rotary potentiometer, and it had 350 degrees worth of movement. So that's my input out, right? And the maximum voltage I can get out of the thing is 10 volts. So what I did is, this is the maximum degrees, this is the maximum voltage. Y'all follow this so far? So my transfer function would be out. What do we get out? Volts, right? What are we putting in? 350 degrees. So the maximum voltage over the maximum degrees. So this gives me a transfer function of, let's carry it out to at least 3 decimal points, guys. And we're actually not dropping these. So what our answers are going to be is going to be volts per degree, right? Does that make sense? So what do we come up and get? 10 divided by 350. No, we want fraction. I mean, we don't want, let's give a fraction. We can give milli. We want it in at least milli. We want to carry it out to three decimal points at least. 0. What? 0.28. Okay, we'd say 28 milli, right? Volts per degree. So what should I expect out of my pot if I set it to 30 degrees? Well, what I would do is I'd say my volts would be equal to 30 times my transfer function, 28 milli, and this is going to give me the volts that we would get at 30 degrees. Because it's volts per degree. So what voltage would I expect on the output of my pot at 30 degrees if it was linear? This is milli, I'm sorry. I left off the milli. Can't leave that off. Not watts, we're dealing with volts. It's volts per degree. So about 800 what?
840.
So about 840 millivolts is what I would have. So now I've got what voltage represents what degree, right? You understand? So what if I measured 1 volt? What degree would that be equal to? So I measured 1 volt out of this. So what would be my degree? Well, it's got to be greater than 30 volts because you understand. So 30 degrees gave me this. So I know it's got to be greater than 30 degrees, right? You understand that? So what do we need to do? So what over here I'm going to do is we're going to say, so transfer function equals volts over degrees. Okay. So we're going to come up here and put this in put it transfer function equals to volt over degrees. All right. Now I can solve for anything. So my degrees would be equal to my volts over my transfer function. It's just basically a 3 expression, right? Y'all understand that? So what did we do? We took this formula right here, and now we can transpose it for what we need. So this is going to be volts over degrees. So I've got 1 volt over my transfer function, right? You understand? What's my transfer function? 0.0028 or 28 milli, right? So we should expect an answer bigger than this because we did this, 30 degrees was 840 millivolts, so it's going to be up in the 40s, right?
Yeah, 34.
So see how we took that basic formula and rearranged it? So how did we solve for this? Well, volts, right? You understand? So volts would be equal to transfer function times degrees. Degrees would be equal to volts over the transfer function. The transfer function is equal to volts over degrees for this situation right here. Here we're using volts, but this can be, volts will probably be down here, but it might not be degrees. It might be per inch, or it might be per gallon, or something like that, right? You understand? But we could take that and put it in our little triangle thing up there and come around and solve for anything we need. That makes sense? Guys? Yes or no?
So once you find the transfer function,
yeah, so what we did was we solved for V. So once this is my formula transfer function, in this class the odds are it's going to be volts on top, right? And then what's going to be over here? Degrees or gallons or miles or inches. And this is the transfer function. So how did we solve for the transfer function? Transfer function was equal to volts for the unit that we're bringing into it. And we came up and got that 28 millivolts, right? Understand? Now, once I've got this formula, I can say, what do I need to do to solve for volts? You cover up what you want to solve for, and they're side by side, so it means we multiply them together. So if I want to find my volt, I take my what? My degrees and multiply it by my transfer function, or my transfer function by degrees. And you come up and got this right here. Right? You understand? So let's say I measure a voltage, and I want to figure out what degrees that is. Well, my degrees is going to be equal to my volts that I'm reading over the what? Over the transfer. So this is just what you learned. It's all the law, basically. So what's nice about any three-term equation is you can put a three-term equation in this guy right here. And then once you got it in here, then you don't have to worry about, I multiply both sides and divide both sides. You just do what? You just look at this and you can transpose the equation real fast. Y'all did this in DC, right? So the transfer function is the ratio of what we're putting out to what we're putting in. If it was a current loop, then up here would be, we would get current out over what? Over degrees. We'd be getting that kind of stuff. So that's same old thing. Are we okay? Yes? No? So position sensors, potentiometers, are we okay with pots? Yes or no? By the way, when you get a pot, you got to be careful. We got two types of pots out there. We got audio taper, and we got what we call linear taper. When we say linear in electronics, what do we mean? Yeah, the ratios vary in a straight line, right? So Ohm's law is basically linear. You know, if we say I is direct with resistance held constant, then I is directly proportional to V. It means it's what? Directly proportional means it's going to vary in a straight line, right? Audio taper, these pots are what we use in stereo equipment. The human ear is not linear. The human ear runs in decibels. So basically it takes double the power for you to hear. You have to go up a power of 10 for you to detect the double in volume. So these are what we call audio taper pots. They are not linear pots. Their resistance are not linear. So if we say a 10K pot and you had an audio taper pot, I said, what would you get if you set it in the center? You know, on a linear pot, you would say it'd be 5K, right? Between the wipers. But an audio taper. So if you replace these things, make sure you get a what? A linear taper pot, right? Slider and wiper, everybody understand that term? Transfer function. Basically, it's using a 3 resistor loading area and linearity. Now, the problem we have with most sensors is that they are not perfectly linear. So one of the things they'll tell you in your data sheets is it will give you what they call the linearity. It'll be like plus and minus 1%. So these guys are pretty accurate, but there's nothing that exists that is perfectly linear, right? You understand that? And also, what we have to do when we load these things down we have to make sure they go into an extremely high impedance circuit. So what I'm going to do is I'm going to draw my pot like this. And let's say we have it set directly in the center. And I have 10 volts. And let's say this is a 10K and this is a 10K. And we'll make my measurement right here. So what would that measure? This should be just like this, no solving, no nothing. Kirchhoff's law, voltage law says we know that resistors of the same size drop the same voltage because current is constant in a series circuit. We know that both those resistors have to drop the entire voltage. So what does that mean? Each one's going to drop 5 volts. I'm measuring across this one, so hopefully we're going to measure 5 volts. Well, what if my meter had 10K ohms worth of resistance in it? Well, if that's 10K, then now we got a series parallel circuit, and that bottom resistor is not seen as a 10K anymore. That bottom resistor is seen as a 5K. So what we'd end up with is we would end up with this, and so instead of 5K, right? You understand why? Yes or no? That's a parallel circuit. Okay, it's a series parallel circuit. So what I would have to do, and I know, and this was a little fun when we're doing this fast, this was something you should have learned in DC, that if you got 2 resistors in parallel, right, you can take, if they're the exact same value, you can take the size of one of them and divide it by the number of resistors in parallel, but they have to be exactly the same size. So I got a 10K and a 10K. So I take this 10K, I divide it by 2, why is that? Because there's 2, so it's going to be seen as a 5K. So that's why I chose resistors of the same size.
No, I don't remember that.
Remember?
I don't remember.
You did? But they got to be
like 2 years ago.
they got to be the same size, right? You understand? So if this was a 3K and this was a 10K, then we would have to use that reciprocal of the sums of the reciprocal things that you've already. So what we're talking about is we were expecting what? 5, but are we going to measure 5 now? So what would measure? So this is going to be 5 over 15, which is going to be 1/3. So we'd measure what? 3.33 volts right there. And we're expecting what? 5. Don't understand how I did that. Because the ratio of resistors. So this is what we call a loading error. So when we set it at halfway, we were expecting 5 volts, but we're getting 3.3. Why? Because we loaded the pot. So what we're saying when we use this pot, this guy that we connect over here needs to be really high resistance. So this is why your meter don't affect it much. Most meters have at least 10 megohms worth of resistance. So if I calculated that, this is going to be measuring 4.9999 volts, right? You understand? So what we're talking about, there's no way in the world I can connect something to the center of the pot, the wiper of the pot, and not have some type of what we call loading error. So there's no way in the world I'm going to connect something that's got infinite resistance to it, right? You understand? But if we got really, really high resistance that we're connecting the pot to, then it's going to be really accurate, but not perfect. So we call this a what? Loading error. Yeah, so this is why when you take your ohm meter, and your ohm meter is a resistor. Your voltmeter is basically a resistor that you're putting in parallel with something. If you put it in parallel with something, so we have a problem with a voltmeter. There's one class we teach where we're trying to set up a voltage divider and we're using a 10 megohm resistor. Now that meter means something, right? You understand? So The smaller this is, the bigger the ratio. We call it the 10-to-1 rule, by the way, guys. The 10-to-1 rule says if what you put in parallel is 10 or greater than this, we ignore the big guy because it's just not enough error to calculate. You understand what I said? That means in a series circuit, if I got a 1K in series with a 10K, then if I'm using the 10-to-1 rule, I say, well, it's 10K because it's over what? 10. Now, it's not going to be perfect, but not most of the time it's what? It's perfect enough, right? Because why? Because we're dealing with so many tolerances. When we say that a 10K, when we say this is a 10K pot, what's the odds of it being 10K? Slim to none, yeah. So every device that we have has what we call a tolerance. And so that tolerance is well within the what we call the 10-to-1 rule. So here, this is well over 10-to-1. This is 100-to-1. So I mean, if it's 100-to-1, I'm going to totally ignore what? That guy, this big over. And that's why with a meter, you can measure stuff and not affect it unless you what? Unless you get into something that's high and put feet. We had some circuits out at US Steel running a number 4 galvanizer line, and it used a special circuit called a mag amp. And it was extremely high impedance, but it was a sensor that sensed the speed of the line. We had a guy in there, went in there, and he wanted to measure that with his voltmeter. As soon as he put his voltmeter across that mag amp, the whole line shut down because it thought it oversped. It thought it was an overspeed. So what he did though, he loaded the mag amp down with the what? With his meter. So meters, guys, meters, even voltmeters, we think they have infinite resistance, but there's no such thing as infinite resistance. And you can measure the resistance of your voltmeter. If you get another meter out there, you put your meter on volts, and you take a voltmeter, ohm meter across that, you'll see what your meter has as far as putting it in a circuit. Normally 10 meg is really, really high, and it has no effect on the circuit at all, right? You understand that? But there are some situations you have to be careful in. Luckily, I might have told y'all the story. So the houses were, the control houses were real big. And what it did, it had a panel down this side, and then it had a door you went in. And Dennis had come in, and he was inside this door, behind the door. And he hit that mag amp and shut the line down. All these big foremans come running in here. And guess where Dennis was? He was in that little thing back here. And nobody knew it was there. Dennis didn't say anything. And they was trying to figure out what shut the line down. And they reset the line and it come on back up. Dennis waited till everybody got out. Then he come on out. So yeah, true story. True story. Dennis Ramsey used to teach here. I don't know if anybody worked out at US Steel knew Dennis. Dennis has probably long been retired, but he was a sharp cookie. Single turn pots. So pots are going to be either rotary or they're going to be linear, straight line pots. The problem with these pots, these single turn pots, is you don't get 360 degrees. Can you see why? Yeah, you got to get a path to get to the wiper, right? You understand? And you got to have these connections. So what we end up with is we ended up with this gap right here. We still call it a single turn pod, even though you can't get 360 degrees of it. That's why I go up at 350. It's actually usually over there. We have multi-turn pod that basically works on a little different. Normally, these guys have a linear pinch pod in it, and then it's got a wiper. And then what happens is your wiper runs on a slide that's on what we call a worm gear. And what you have is you have a little set screw out here that you turn, and we have what we call 10-turn pots. So 10-turn pots, and these are 360 degrees. So that means you would have 3,600 degrees worth of resolution on these things. So these guys are okay for a lab. But you got to understand, we got 10-turn pots out there. I should have brought some over here, guys. I might try to remember to do that. We got some in the lab over there. Most of my parts are over there. I think we have a 5-turn pot over there. The ones we're gonna deal with is just one per pot. We don't get 360 degrees on that, right? Okay, then. So this is the symbol. So we have the two outsides, and this is where you measure. So if you think you got a 10-turn pot, what you want to do is you want to measure between 1 and 3. But you can't see the markings on the pot. And if it's a 10K pot, which is what we're going to use, right, then is it going to measure 10K? No, but it'll be close to it, between 1 and 3. Now what varies, and so this is where we're going to connect our output right here. Right? You understand that? So these two ratios are going to vary, right? You understand? So if I move this thing all the way up here and measure across this thing, it's going to measure 10K. If I move it down to the center, it should measure what? 5K. But what you're doing is you got 5K up here and 5K down here. So if I move it down here, I might measure 3K between 1 and 3, but between 2 and 3, but if I measure between 2 and 1, it would measure 7K. Don't understand why? Or whatever Okay, so what we're doing is we got two options. We got this option right here. So I can put my wiper all the way up right there. Okay. And then I'm going to put my ohm meter right here. And then, of course, if it's a 10K pot, then I'm measuring across the pot. It's going to measure 10K. That's between 1 and 3. Then when we turn it into the center, what we're actually doing is we're setting up a 2 resistor voltage divider like that with my wiper right there. And I know I have 10K. I know I have 10K between 1 and 3. Right? You understand? So if I measure between here and here, I measure 10K. So if I come over here and I measure 3K right there, I know my RT is 10K. Then what's the top one got to measure? It's got to measure 7K ohm. So the sum of the two, so if I measure between 1 and 3, it's going to measure something. I'm sorry, if I measure between 1 and 2, it's going to measure something. If I measure between 3 and 2, it's going to measure something, and the sum of them, it should be pretty close to 10K. So what you got, guys, is this is a 2 resistor voltage divider, but what's nice about a potentiometer, it is a variable voltage divider. So if I needed 5 volts out of 10 volts, then I needed exactly 5 volts at that situation, it would be impossible for me to get 2 resistors that would give me that, right? Because I might use 2 10K resistors, but what's the problem? Those 10K resistors are not going to be the same. But with that pot, I could take my voltmeter on that wiper and I can turn it until I got exactly what? So half of whatever I want, right? You understand? So what a pot is a variable voltage divider. If we move it all the way to the top, and it varies, and guys, I should know this, but it depends on what, clockwise or counterclockwise. Well, if clockwise causes this resistor to go down, right, you understand, then counterclockwise would cause it to go up, right, you understand. So it depends, so when you take the output, you can make one common or you can make 3 common. One of them is going to increase going clockwise. The other one will increase going what? Counterclockwise. And I should know that. So it all depends on you. Normally, we like things to increase when we turn it clockwise for some reason. But it doesn't. So what we can do is if I come over here and have my pot, and let's say this is 1 and this is 1, this is 3. Well, if I adjust it all the way up, then I get whatever voltage I have connected to 1, right? You understand? If I turn it all the way down, then I'm going to get 0. If I'm somewhere in the center, I'm going to get a voltage between what? What I apply to pin 1 and what I apply to pin 3. That makes sense? Yes or no? Well, what if I have 24 volts available and I got my pot? This might not work out, but it's going to be close. And I want my pot to vary. When I got it up here, I want to measure 10 volts. And when I got it down here, I want to measure 0. But I've got a 24 volt supply. We have this same problem. We have a to D converter on this little PLC right here. It's got an A to D, and it's looking for a voltage, and I don't have a pot in here. It's looking for a voltage between 0 and 10 volts. It powers up off 24 volts. So I wanted to make my pot vary from 10 to 0 instead of like 24. So how would I do that? Let's see, I need something to drop a voltage when I put current. What drops the voltage when I put current? Resistor. So I would come up here and I would take a fixed resistor. And like I said, this might not work out perfect. Okay. Now this is 10 volts at 10K. So how much current would that be? So it's going to be, so the current through here, that's going to be 10 volts divided by 10K. And what would be the current flow that would go through that pot there? So this is my pot there. I is equal to V over R. I got it down there, guys. So what would I be equal to? So if I put 10 volts at the top of a 10K pot, this is the current that's going to flow through it, right? You understand that? Yes? What's that? 1 milliamp. So I need a resistor that drops 14 volts at 1 milliamp. $14K, right? So if I get a 14K resistor, and so what we're doing is we're establishing what we call a span. So we're establishing a voltage that's not available to it. It's always got to be lower, right? Y'all understand? Yes or no? Well, I can't make it higher than the 24 volts. So I can't say, well, I need 50 volts here, and I got a 24 volt supply. So if my supply is bigger, then I can always set the voltage I need right there, right? You understand that? Just by putting another resistor in series. So now I should be able to do 14K, if I can get a 14K, and then I should be able to adjust it between 0 and 0. But we could do it another way. Let's say I needed to adjust it between 10 and 3 volts. So I got a pot. I want 10 volts right here. I want 3 volts right there. And it's a 10K pot. 10K, Rich. So how much voltage is that pot going to drop? 7 volts. So I'm going to say I would be equal to 7 divided by 10K, right? Be 700 microamp. 700 microamp. So I need a resistor up here that's going to drop what? Got to be the sum of them, guys. Huh? What's that? I'm going to have to put a resistor down here. You understand that? I'm going to have to put a resistor up here. This guy's got to drop 7 volts. 7 volts, Reg. It's going to drop 7 volts. This guy's got here going to drop 3. We have 24 volts up here. So how much does this guy got to drop? 10. I know the size of this resistor, but now I know everything now, right? Because I know the size of this resistor, and I know how much. So we could have got. I know the size of this resistor. I know it's got to drop 7 volts, 700 microamps. So now I need something that drops 10 volts at what? 700 microamps, and I need something out here that drops 3 volts. And then we've set it up so we can have a span of between 3 and 2 volts. Everybody understand how I got that? Huh? That's right.
The print off the voltage you're supposed to add up each one of those volts.
Well, y'all gave me 10. 9, somebody gave me wrong. Thank you. Who said 10 votes? It wasn't me. Yeah.
You know, the cells would be 14.
14, thank you. Somebody just wanted to, now I didn't write it down. Y'all, somebody called out 10, but you're right, I should have caught that. I should, y'all always should have that.
Yeah.
So whoever called that 10 votes was just trying to see if y'all were paying attention. You're right. So 14 volts at 700 microamps. We already got this. We know what this guy is, and then 3 volts at 700 microamps is a series circuit. Now, this is my pot right here, by the way. I drew it as a resistor. But when we calculate it, we treat it as a resistor, right? You understand that? Now we got to make sure this guy right here is really high, a very, very high R, right? Or we'll have a loading effect. What did y'all get for the top resistor? And we're going to calculate perfect, guys. Let's not worry about it. We in real life, if we use standard resistors, we'd live with what we got. If we needed exactly what it was, then we would use rheostats inside the thing. But odds are we're not going to do it. What do we get for the top one? 14 volts at 700 microamps. And then 3 volts at 700 microamps. I don't know. I'm just writing down. R is equal to V over I, right? 4 point what? 2A.
Okay.
Okay. So we're going to do something like this in the lab. We'll use the full pot, and then we're going to set the span with 2 resistors. If we can't find the 2 resistors that's on the lab, we'll find 2 resistors that'll work, and we'll just rewrite the lab over there. I meant to bring the resistors over here, but and I said they teach DC over there. We don't have to leave this.
Do some of that last now.
Huh?
Did some of the.
Yeah, but we need a 3.3K, and I'm just looking. I couldn't find it. So these are just different. This is the pot I was showing you about. These 10-turn pots, these multi-turn pots. I don't know how many turns this is. You can see it's got a racket beam. I'm turning this and it's turning this, and the gear ratio is here. This guy would take 10 turns for it to move. So this is what we call a linear pot. Physical, not linear type. These are multi-turn pots. Those are gang pots up here, so you can actually run into where you have multiple pots with the same operator. Okay? Next. So this is basically showing how this thing works. Showing the ratio between A, B. They're calling their leads A, B, and C. If one ratio goes down, the other one's going up. Connection of a potentiometer. So this would be one example where we got a potentiometer connected to some type of motor. They're saying it's a 350 degree pot. They say that, but as of yet, we never got a pot that goes 350 degrees. This is basically what we just talked about. I don't know how many rotations the pot is. I don't know if it's a multi-turn pot or a single-turn pot. Now, that's something you got to be real careful with. I need to find that. I've got a little motor. I don't know if I need to find it. It's a motor. It's got a pot you can turn on one side, and the motor starts turning until it lines up. Make sense? Okay? A pot is supplied with 10 volts and is set to 82 degrees. The range of the single turn pot is 350 degrees. Calculate the output. We've already did this. 10 volts, 350 degrees. We know the transfer function is 28 milli, right? So transfer function is equal to what? Yeah, transfer function is equal to, let's do it like this, is equal to volts over degrees. So here I'm giving it a what? So the degrees would be equal to the volts divided by the transfer function. Right? So, oh, we're not solving for degrees. What are we solving for? Yeah, so we're solving for V. So V would be equal to the transfer function times the degrees. Okay? So V would be equal to our 28 milli times 82, and that should give us our voltage. So once you get your transfer function, then now the voltage means something, right? In your control system. So your control system could do the math. Is that right? Everybody okay? The 28 milli is right. So what we got? 2.296. 2.296. Okay? Well, okay. See how you did that. Sounds like a good test question. I got 2.35. 2.8. Yeah, this is what y'all did. Y'all rounded. Or say we did that. So y'all rounded right here. So when you round, so y'all said 0.28, but I got 0.286. Well, if you round this, it's not going to round. This is not going to round to an 8. This is going to round to what? A 9, right? I know how to run. What's the rule of rounding? 5 and up, you round up. 4 to 0, you round down, right? It's not too bad though. We talked about loading error, right? We did some math, so we're going to go through this. So that means if we're going to use a pot, we need to make sure that whatever it feeds into has a really high input resistance, right? So if it's like it's 100K, then it's going to do what? It's going to load it, right? So we're not going to get out what we expect. My loading was lower. It depends on what you're going for, right? So here we was trying to calculate the what? Okay, so first of all, we would calculate our transfer function. So our transfer function is going to be, what are we getting out? Volts. What are we putting in? Degrees. Right? And this gives us a transfer function of 0.0 something. Well, that's what we used. And that's why we got to be real careful on this, on how much we round. And you got to round correctly. Rounding is just not dropping digits. Rounding is the rule of rounding is if the preceding digit, and we have to round toward that. So if I take 10 and I divide it by 300, if I divide it by 350, That is not 28. Okay.
29.
If we wanted to round it to 3 decimal points, in fact, this really rounds because this is a 7. If this is a 7, it makes this a what? 6. If this is a 6, it makes that a 9. Okay, y'all understand that? And then if we took that, if we took the 82, and then we multiplied that times 0.029, that makes sense? On my answer though, I rounded four. Which the more decimal points you round to, the more accurate it is. There's really no need to be that accurate. So the problem we always run into in electronics is our math is perfect, but our components are not. Right? You understand that? And of course, in DC, what did they make you do? Well, DC, they made you measure your resistance. You use the measured value to calculate Ohm's law, and you notice everything was extremely accurate. After that, we don't do that anymore, guys. We just understand that our calculations and our measurements are going to be a little bit. They'll never be what I'm saying. Now you get into solid state, guys. We do a lot of approximation. So we get it close enough to know if the thing is bad or if the thing is good. Because there's some things in solid state that varies with temperature. You've got things that vary with temperature. So if you wanted perfect calculations, you would have to go through some calculus formulas to figure out the resistance of a silicon junction at a certain temperature Kelvin. Or you can use 25 millivolts over IE and approximate it, right? You understand? So we okay? So this is what I got, but notice what I did. I rounded to 3 digits. I'm sorry, 4 digits. In fact, what's the rule that we use? Once you convert it to engineer notation, we want you to round to 2 decimal points. Why did you take it over as far as 1 decimal point? So in solid state, we say as soon as you convert it to engineer notation, 1, 2, 3, then you round to 1 decimal. Just to make this one right. Isn't that what we teach? Yes? I think in DC we round to 2 decimal points. I can't remember what it is in AC, but solid state we round to 1 decimal. So what would be the transfer function? You understand gears. What do we do with gears? Well, we can turn things without gears. What do we use gears? Yeah, but we got 2 things. We got work. Basically, work is equal to work in and work out is equal to each other. So work in and work out would be equal to each other times the efficiency of the system, and the efficiency of the system will always be less than 1, right? There's nothing. So just for work's sake, we could figure out, okay. So what we're saying is if work is equal to, what is it, speed times distance? Here we're using torque. And my work's in torque. Well, what that means, no, this is not what I'm trying to get the form in my head. That'll work off. So if work is equal to speed times distance, then the speed goes up. Nope, this is not right. work is equal to force times distance. There we go. So that means if I go over here and push against that wall, when am I doing any work? Why? We're not getting any distance. A lot of people don't understand that. So what happens if distance goes up, then force has to do what? Go down, right? You understand what we're doing? Okay. We're talking on the output. So we could also say work and distance, work and speed, so force times speed, because, right? You understand that? So the faster you go, the further distance you cover. So what happens in here, this would be torque times speed, because we're dealing with something moving in a circle, right? You understand that? So that means if I'm coming over here and on my output, if I increase the speed, if work in and work out equals each other, what has to happen to the amount of torque we can create? It has to go down. If speed goes down, torque goes up. Right? You understand that? So if I have a little gear feeding a big gear, then what's going to change? So that means for every time this makes one revolution, this over here might make a 1/2 of a revolution. Right? You understand? So my speed goes down, my torque had to go up. Right? You understand that? Anybody that drives a car understands the transmission. So what we start off with, we want to increase torque to lower speed, right? You understand that? So we start off with a little gear feeding a big gear. Right? You understand that? But as we move through our gears, what happens to our ratios? They start changing because we need a lot of torque to start a car moving. Why do we need a lot of torque to start a car moving? Yeah, anything at rest wants to stay at rest. Then, of course, once you get it up in speed, then it takes a lot. We can shift down and get more close to we don't ever get to the exact speed unless you got a drag racer that's got 24,000 horsepower out there, right? Or 2,000 horsepower. Those things don't run much of the transmission. So what we do with gears, we can change the direction of rotation. But what we do with gears, we either use them as speed multipliers or we use them as torque multipliers. So here what we're doing is we got a pod over there. So we're going from big to little. So what would we be doing there? So here's my motor. So this is my input. My input's my motor. It's going to turn 90 degrees. That's the max. This guy right here is going to turn 90 degrees. How many degrees does that guy go? How'd you get that? We should. So my gear's 3 to 1, so that means for every one turn it turns. This guy up here, I'm sorry, for every 3 teeth we have down here, we have 1 tooth up there. So that means this guy's going to be turning 3 times faster. So it'd be 90 times 3, and that comes up and gives you what? But it's going to be doing it at what? Is it going to be rotating faster or is it going to be rotating slower? The pod.
Did that, slow.
Well, this guy's turned 90, that guy's turning 270.
Oh, he's going fast.
It's turning faster. It's going to turn 3 times faster than the motor. So whatever the motor runs, it's going to turn 3 times faster. Right? Understand? So what would be my transfer function? It's not going to be the 90, because the pot never sees 90. The pot's going to be what? 270. You understand? Yes or no? So if I knew the voltage applied to the pod, I would divide it by 370, and that would be my transfer. That would tell me the degrees of the pod that turns, then I would divide that by 30, I would divide that by 3 to get the degrees of the motor, right? Does that make sense? This is what we on the test.
So we just assume the voltage and then find a transfer function.
We could assume a voltage. It would be better to have the actual voltage of the system. So if we had 10 volts on the pot like before, then my transfer function, and the maximum it's going to give me is what? 270. And 270, we would set it up so 270 would give me 10 volts.
I get 37.
Is that rounded to?
Yes, 37.
Okay, so 37 milli, right? You understand? Okay. So what would be the degrees of the motor if I measured? Now it should come out to be 45, right? So I'm gonna come up here and let's say we get 5 volts out. Keep doing that. So my degrees is going to be what equal to what? My degrees is going to be equal to 5 over 37 milli. What we got? 135 degrees. I'm going to divide that by 3. What's that? 45. Yeah. See what we did? So going the other way, so we multiplied going to the fast side and we divided. But see, I need the answer. That's why I took 45 degrees. Y'all heard me say we should expect what? 45. Huh? Because what we're doing is we're going from big to slow. This thing is running this guy is running 1/3 of the speed of that guy. This guy is turning 1/3 of the distance of that guy. And this is a speed multiplier. If we go from little to big, we're doing a torque multiplier. If we go from big to little, we're doing a speed multiplier. The torque is going to go down exactly what the speed. So if that guy's right there is running 3 times the speed, then it's developing 1/3 of the torque. So what do we use gears for, guys? To increase the torque we need. Of course, we sacrifice speed, right? To get a torque increase, we have to sacrifice speed.
Just like a bike.
Or just like a handrail. I mean, you got a handrail in your hand. You hear that thing's in the output is barely turning because it's a what? It's a torque multiplier, right? So your motor's in there. We got a motor in here. It's in here somewhere. It's got a 64.5 to 1 gearbox. That means when the motor turns 65.5 revolutions, the output shaft on the turn 1. But what we're getting is we're getting what? So my motor. So my motor is producing 65.5 times more torque than over here. So that's why over here you can spin this with your what? Finger. Try turning this guy. Because here we're going backwards, right? You understand? You can't turn it here, but you can spin it like that. But I would have to turn this what? 60.5 revolutions for this guy here to make what? To make 1. So this is a torque converter. So since I'm decreasing the speed by 65.5, I'm increasing the torque by 65.5, right? On whatever this little DC motor in the back. So here's the gearbox right there. So see if y'all can turn this side right here. See if y'all can turn it. So that's how you can pull that big old 2,000-pound car. You can make it start off a red light, right? You understand? Because you start off with a torque multiplier. But if you got a straight shift and you don't shift gears, your motors will be going.
Where do you get that fire from?
I made it up.
Oh, okay.
I said, what would be the degrees if I measured 5 volts? Right? So we had 10 volts for 90 degrees out here, right? You understand? So 10 volts up there for 90 degrees down here, but we did a speed multiplier. So you can see I can use a pod even though I've got something making multiple turns. So, but I could run it real slow. So I could have a little small gear on my motor and have a big gear out there on my pod, right? You understand? But it'd be less resolution, but sure.
Okay.
So I can make a pod. I can make a motor run 100 turns and the pod might not even turn one time just by using a watt. Use a torque multiplier, but a speed divider. Analog to digital converters, guys. Most current controllers. No, we went past it, but let's go ahead and take 10 minutes right there.
I got an email from
I'm gonna try
the
to, huh?
The MSCC guy.
Huh?
I got an email from the class will be on Monday night. It ain't gonna be on Friday morning.
Well, he said there's gonna be a Friday morning class too.
Well, not for the email, just something.
He might
He
be
said he was gonna do a
Friday morning and a Monday night.
Oh, it is?
It's supposed to be like a 9 a.m.
I think Mr. Sanders is doing the morning class. So send it back saying I heard there was going to be a Friday morning class. Can I get into that one?
Wait a minute.
Of course, that might be.
On yours, Thursday, 21st. He sent me Friday, March 22nd. Read it. He sent you another one? No, that's the one I just showed you. He just sent me one that said Friday, March 22nd. Check his spam. He was going to his spam box. Yeah, I was on my spam. Check his spam box. Oh, I know. That's fine. Oh, look, yeah, he must have sent you the wrong one.
Well, no, he's got 2 groups. He might be trying to balance the groups, and he's putting you in a class to balance the group. That's the only thing I can say.
9 a.m. to 1 p.m. class, 12 p.m. class. Oh, no. Yeah, on Friday. That doesn't say what day.
This email is referenced in certification on Thursday. I will be in the welding class to register you all in the course. I will be there for May. I will also be on campus Thursday night at 5:30 to 3 p.m. registering students for the Monday night class. If you signed up for the Monday night class, please meet me in the alcohol building, room H107. The certification class will consist of 4 areas of concentration.
I'm gonna go see him Thursday night.
I think it says if you signed up for the Monday class. They don't say you did.
Yeah.
But he don't mention how to get into the Friday class.
At all.
I would send him an email back and say, are you offering a certification on Friday? I can't make this, but are you offering a certification on Friday? Let me go down here and see if I can run off this. We need to do this before the
Hey, what time on Thursday is he gonna be there? Yeah, on Thursday. Yeah. Yeah, the boy can get the boy. They say, Gabriel, this guy really I come up. He does like, huh? He does. He's like, it looks like he made them all around. Oh, that's you doing right there? Lay right in the blue shirt? Yeah, she's so good. She had the hunt with him too, boy. She gonna tell that with you. I bet he's gonna bring it. Yeah, I did both of them last night. Her class and some other dude. Yeah, he is thinking of that. She ain't shape too. Oh yeah, she is. She'll be down there. No, what? She does like 22 push-ups. The little, what's that, a survivor awareness thing? Yeah, she does. Like grown men push-ups. Yeah, and she's like, yeah.
like, all the work you have to do for a class, you can get it done like in the first 2 weeks. And all you have to do is match it.
Got an interview tomorrow, man. In Wichita, so come work from the state. The Bayside, Michigan. Yeah, I feel this month, man.
The one, the new one they do?
No, so they got one in Wichita called Motortech. They just built that one. But this one here, it's called here based out of Michigan, man. They get metal to come in and they have keep the metal oil selling for a rush. And me as a maintenance technician there, I just work the PLC on it. Whenever the PLC has a little problem, I just troubleshoot the line on it. Yeah, then I got things for Honda Friday too. I thought they didn't get on LinkedIn, man.
I'm gonna get
Yeah,
on
you need to get on we have a partner, man. He told me to get on LinkedIn last month. I didn't want to bro, you know? Nah, man.
which couple you got? I can't even do it.
Where the money is, right? Where the money? You move to the money. You move to the money. Yeah. You got it too? You know, money night. They said Friday morning, I was all for that.
That was the same Friday.
You got Friday here?
Friday morning.
Yeah, mine said Monday.
For break. What time is it?
I love the bush for that, boy.
Oh, yeah.
It's like 8 o'clock.
Yeah.
Bush,
What is it?
robotics operation. Operation program. 8 o'clock. Love it.
What? I'm just gonna cover my spine.
Someone bring got any food, I can fit it, boy. And that's what that's the test. Talking about, okay. Oh, you want to do that for free? Yeah. Hey, but room on room back there.
My head double take one of those.
Oh, bro.
Eat today.
Come on, Foster, you ready to Foster now?
Yeah.
Well, I thought the number at 116 on Foster's now, boy.
I think I gotta be in that about to look on school.
You got D in?
Yeah, that's what it is.
Trying to do it, hey. No, Foster won't fit it. You thought crazy though, bro. He ain't gonna fit it.
Oh, well, you can get me.
You know what's up, man. tell you, when you put this class in digital, you get the long certificate. You graduate, bro. You get the paper right there for it.
Yep, long.
Yeah.
Just take it easy, bro.
Nah, so,
Everything else, all that stuff that's left, some. But this was the last, get five off. All I can do is, I hate to take the math, one.
if you had the social, you get two. One is 5:32. And then on Friday, it's 9 o'clock to 1 o'clock, and then, 12 to 4. Yeah, I just got it. Well, I saw an email, you sent me. Thursday, so we're gonna be, 5:30, actually, 1 day. Good, good.
Pretty simple, plus sign it, date it, and then the store cashier, pay that amount. And that turn into registered document. Nancy will put it in your packet. Or I don't know if Nancy gets it first. I'll let this thing recording, so we gotta be careful. Not the first time I've done it. And unfortunately, it won't be the last. Huh? Yeah, it's not hard. Okay, A to D. So we know that most current controllers are digital devices. Digital devices don't understand analog. So what we have to do is we have to have a device inside the device called an analog to digital converter. Analog to digital converter, or an ADC. Now, a lot of our sensors, the actual sensing element itself is analog. And what do we mean by analog? What's analog? I'm waiting. So what's analog? Nobody here knows what analog is? Give me what you think analog is. You're looking forward to trying to read it somewhere. So analog is a signal or something that continuously varies. And it can vary when we're dealing with voltage, it could vary from a minimum voltage to a maximum voltage in an infinite number of combinations. So anybody that tells you digital is more precise, they don't have the idea of what they're talking about. Digital, we're going to have to be limited by a certain number of bits or digits depending on the system that we go into. Y'all probably heard 64-bit, 32-bit, stuff like that. Well, if I got 64-bit processor, then basically that's where it's limited to, right? You understand? So we can't deal with infinity with digital. It's just like I can't deal with infinity in the decimal number system. Can anybody write what number infinity is equal to? You don't. I mean, you could start counting now, so we don't understand infinity, even though analog can vary in infinity. It's just like time. We break time down in seconds, but time varies an infinite number of increments between what? Every second. We talk about milliseconds and picoseconds and nanoseconds, right? You understand that? But it could vary. We talk about volts. Volt could vary in an analog voltage could vary an infinite number of combinations between each volt. So if you're going to be precise, then it seems like analog would be the way to go. But the problem is that we got to be able to transfer this information. We got to be able to process this information, and we got to be able to store this information for further use, right? And we can't store analog. So what the advantage of digital has is that, and the analogy I use is I've got a light that I can vary. Let's just say, let's make it digital. So let's say I've got a light that I'm trying to vary, and I've got 10 different brightnesses I put on there. So minimum brightness or off would be a digit 0. And then when I turned it on its brightest level, it would be equal to a 10. But I'm going to go in steps, right? You understand? And I come up here and I said, okay, guys, these are the brightnesses. I point them at you and I shine them. Okay, so I'm going to send you a number and I'll start flashing this thing. How many of y'all think in this class y'all would all write down the same number? Right. And okay, I'm running voltage. What happens with voltage? And then, let's say I go across a lot over there. Now we're going through some impurities and my brightnesses are not the same. So what was a 10? Now you think it's a what? It's a 9, right? You understand? And then my batteries and my flashlight going down a little bit. And what the brightness for a 10 was the brightness for a 5. So that's the problem we have with analog. And plus designing circuits that we can do math with. If I want to take this and add it to that, analog's almost impossible to do math. Logic, ands, ors, nots, nands, nors. It's almost impossible to do it with analog. Saving it for future use, it's almost impossible to do that with analog. So the advantage of digital, guys, is that the circuits that process it are relatively simple. We can transmit it over great distances. The analogy I use is I've got a flashlight and I'm either turning it on or off. It's like the Navy. You know, when the Navy, when they want extremely secure transmission, they don't send it through the air. Those ships will point them lights at each other, right? You understand? And they flash them. How far can the ships be apart? As long as they're not over the horizon, right? You understand? And they'll be able to see the lights. So we can send digital over great distances and maintain the integrity of the information I'm trying to send. Voltage, guys, if I'm trying to send voltage, it's almost impossible to maintain voltage over distance, right? We can store it for future use, right? You understand? And we got circuits that do math with it. Math circuits are easy because all it's doing is adding ones and zeros. But we live in an analog world. Temperature varies with analog, right? Light varies with analog. Speed varies with analog. Just by we are analog. We're an analog species. Our brain is an analog computer, right? You understand that? So if I take this analog information and bring it into a computer wants everything in ones and zeros. So we have a device that takes what? Analog to digital converter. Are they perfect? No, they're not perfect, right? Because they can't be. But it gives us a method now that we can convert them over. So we have flash converters, we have assisted approximation. So you got a digital multimeter. It's displaying digits, but it's reading an analog value. So what's inside your digital multimeter? An analog to digital converter. We had the old analog meters, the old pointer meters for years. You had about 5 different scales on there, and you had to figure out what you wanted. Some of them were non-linear. Now, if you want to measure ohms, you just put it on what? Ohm. And it comes up and displays ohms for you, right? But ohms can be anything, but your meter takes an analog value for you and converts it into a digital display, right? So the resolution of the A to D converter depends on how many digits in the binary number system you use. So we're not going to get real heavy into binary. But the problem we have with decimal is each digit on the decimal can have numbers from 0 to 9. You understand that? In binary, it's only what? 0 and 1, which makes it nice. Because now we can represent this thing with either current or voltage. And of course, voltages are more popular to use. So that means maybe 10 volts would represent a 1 and 0 volts would represent a 0. So now I have the ability to represent information instead of trying to use an infinite number of combinations. I'm only using one, 2. The problem we have is the number of, since I've only got 2 combinations per digit, or, well, by the way, in binary, we don't call them digits, we call them bits, but that's the same thing. And then we have groups of 4. Anybody know what we call a group of 4? Most people don't hear this often. This is called a nibble. A group of 8, most everybody's heard about a group of 8. 1, 2, 3, 4, 5, 6, 7, 8. We call this a byte. And then a group of 16 is referred to as a word. So I don't know why they left we always say it looks like people that first came up with hungry when they came up. bit, and then we'll buy. Then they went to Word for some reason. Then after that, we just moved in groups of 16 bits. So 32 bits would be what we call a double Word. Our PLCs called it a long Word. And then we have a group of 64 bits, which would be a quad Word. PLCs called it a double long Word. So after that, we do it. Now, the amount of resolution. So what we're going to do is we got two options. We can have what we call a digital or binary or digital AD converter, which comes up and either gives us a true or a false output. So a lot of the sensors that we're going to be using this semester has a A to D converter built into it, but it's only one bit. It means it's either what? True or false. So what they do is they've got even though the sensor itself is analog, they have this little single bit A to D converter built in. And then what we'll get out of this, of course, we'll either gonna get out of this thing is either what? A true or false. Or a one and a zero, or a voltage or no voltage. Of course, here our sensors are 120 volts. So if it's true, it's going to give us what? 120 volts out. If it's not true, it's going to give us 0 volts out. But it's going to be analog. The sensing element itself is analog, but the A to D converter is in there for us. Inside the computer, they've got a multi-bit analog converter. So with 8 bits, we could take a signal and we could split it up into 255 units. 16 bits, we can go 65,535. Another thing that was very confusing in Germany, guys, is Germany uses commas, uses periods where we use commas, and commas where we use periods. It is weird. And their keyboard on their computer is exactly the same as ours, except they swap the Y and the Z key. So a German keyboard is just like ours, but they swap the Y and the Z. Tell me why they do that? I don't know, but it sure confused Rich. And looking at money. So you saw $35, it'd be 35,000. Of course, they were on the what do they call it? The European money. They call it Euro. Yeah, thank you. So inside the computer, it depends on the resolution. So if it's a 16-bit converter, we would take 10 volts and we would divide it into 65,535, and that would give us the number per what we call step. If it's a 32-bit converter, I should have this number floating around in my head, but I don't. I've never seen a 32-bit. This Allen, this PLC has a 10-bit AD converter. This guy's got a 10-bit AD converter. So what's going to happen is we input an analog value, and then it's going to give us a binary number that represents that way. That makes sense? So a 32-bit, which would be a double word, would be 2 raised to the 32nd power minus 1. So if I had a 32-bit A to D converter, and this would be the resolution of it. So if I was inputting 10 volts for maximum, it would be 10 divided by that number right there. The Siemens 1200s that we have, 1214s we have a 12-bit A to D converter in it. Oops, 12 raised to the, oops, I'm sorry, clear, 2 raised to the 12th power equals that minus 1. So it could split the thing into 4,095 different binary numbers. That would represent 0 to 10 votes. Does that make sense? Yes, or no? So what these AD converters, it's going to give us a binary number that represents a analog value. And it depends on the number of bits you use, the resolution of how this thing, the number is going to use. So like this guy here, it's got a 10-bit AD converter. So it can give us it can take 10 votes and divide it into 123 different numbers. 0 through whatever 123 is. So 10 bits. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. So that would be the range it would go through right there. But each one of these would represent a certain voltage, right? Does that make sense? So let's just do that. Let's say 10 bits. So I'm going to say, and we're bringing in 10 volts. 10 volts is the maximum. We're converting this to 10. So 10 bits would give us 1,023 different combinations. As soon as I put my 0 in there. So what would be my step per vote? So this is steps. We call these steps. This would be votes. So the transfer function would be equal to what? 10 divided by 123. Not 1,023. 1023, but that's 1,000. Just the way you say it, right? Let's carry it out to at least 3 decimals. What's that? Milli. So that means if I had 5 votes, so transfer function is equal to votes over steps. So if I measured 5 votes, then my steps would be equal to right, steps, 10 divided by 9.77 milli. And we round this. It's going to be a weird number, but it's got to round to a whole number. So one thing that binary has a problem dealing with in the A to D converters, it doesn't have any fraction. And that's going to be the resolution of it. So 5 divided by, what we say, 0.00977 will give us that. And then I got the wrong thing here. Huh? Did I say that? I said 5. We're getting 5 votes out. What would our step be? So 10, right? So we're trying to calculate the steps. So steps would equal the votes over the transfer function. So 5, I got it on decimal, divided by, oops, no, don't let me do that. So what was it, 511 point what? Isn't it 511? Yes. Huh? 9.77 million. Okay, so I said, what would we get if we had 5 votes, right? So 5 votes, and we're trying to figure the number of steps. That would be 5 divided by the transfer function. 0.00977, which is 512, right? So 512, and this is the binary number it actually gives us right there. So that's what we would bring. That's what the computer would say. Huh?
512 holds the weight back
Yeah, done.
2, 4, 6, 8, 10, 12. Started there.
You start with 2 and move up. I'm sorry, you start with 1. 1, 2, 4, 6, 10, 12. I'm sorry. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. So that's 512 in binary. But this is what the computer would see. Now, fortunately, PLCs know that you don't understand binary, and it's a computer, right? You understand that? So what do you think your PLC would tell you? It would say 512. So, which is really neat. But this is actually, but if we actually looked at the register where the A to D converter was coming in, this is what we'd see. But if we tried to use it, and that's what's nice about a PLC, it's a computer. And computer can make things appear like they're not really are, right? So what would be real neat is that if you was looking at this on the PLC, it wouldn't give you the binary number, it would give you the what? It'd give you 512.
So that's what's up with the count.
What you mean?
Got count on the PLC.
No, this is what we would use, and we would process this information. So I've got a device out there that's going from 0 to 10 volts, and let's say our temperature. So when it's a certain number of degrees, it gives me 10 volts. When it's 0 degrees, it gives me 0 volts. And then I'm measuring 5 volts. Well, my computer would see that as 512. This computer would see it as 512. So we would use this information not necessarily as a counter, but we would use this information. Let's say I needed to turn on a fan if the temperature was over 138 degrees. Well, I'd have a temperature sensor out there outputting this in there, right? You understand? And I would figure out the transfer function. And when it got up to be, 512, we'd turn the fan on. That makes sense? And understanding the flash converters and the way we do it. So the way your meter works, it runs what we call a counter. So that's why your meter, we can buy 2,000 count meters. And if you ever look, your A to D converter, it ranges on 1999. So if your meter ranges on 1999, then it's a 2,000 count meter. And then we have 4,000 count meters. So the resolution on a 4,000 count meter is better than a 2,000 count meter. But you can tell if you got a 4,000 count meter because it's going to range on what? 3,999, right? And then we have 6,000 count meters. 6,000 count meters are going to range on what? 5,999. And those guys, what they're doing, they're running a counter and they're comparing the output of a D to A converter to an analog to digital converter over to the analog value. When they match, it stops the count. And that's the way your digital meter works. It's really not any concern to us whether it's a flash converter, whether it's successive approximation, or whether it's an integrated. All we know is that what it's going to do is it's going to take an analog value and convert it into a binary equivalent. Now the single bit A to D converters are nice because they hit a threshold and they switch from what? True to false. So last semester when you were dealing with that induction sensor, you put a piece of metal up there, the output went true. Even though that analog input might have been giving it a certain number, the A to D converter was switching it over to a single bit, right? You understand? But what you need to do is understand that when we go into a computer that's got an analog to digital converter on it, it's going to give us a binary number that represents that. What's nice about PLCs is it's going to give you the decimal number. But you got to realize over here, this might be 15 degrees, and over here it might be the number 512, right? So you got to figure out that transfer function between what? Between degrees and the actual count that the A to D converter is going to give you. And then you can do the math. So if you know the transfer function, you can take your 512, you can multiply it by the transfer function and and you get the degrees. So now it'd say 52 degrees, right? You understand? So, you didn't take the advanced PLC, right? Did you? Yeah. In advanced PLC, we get into the math functions. We can add, we can subtract, we can multiply. And so we can take a number coming off an A to D converter, and then we can multiply it by the transfer function, and then we can do what? Then we can make our PLC display but display positions, we can make it display what? Degrees, even though the sensor itself is analog. So 512 would mean nothing to me when it's supposed to be what? Degrees, right? Does that make sense? So we could take, so what we could do is we could skip over the volts and we could say, okay, this number of degrees would give us a count of 1,023, right? Does that make sense? And then we could use that, or we might go to 2. But that's what's important about being able to calculate the transfer function, is because, like I said, a PLC, if you display the output of the AD converter, that means nothing, right? Unless you know what that means. And then you can do the math. You can tell your PLC to do the math to actually convert it back to the actual unit that you're trying to make.
Question on another spot, I don't work all the time. 1,023, you just divide that by 2, that don't always work.
But no, I just did it. That was me. I said, okay, 10 volts, 1,024 steps, right? You understand? I said, what would I get if I measured 5 volts? So I'm the one that came up with the 5.
Okay.
And I expected it to be 512 because that's what I expected it to be, because that's about 1/2 of 1,023. So you're right, I could have divided it by 2. But what we were trying to do is figure out what count I would get if I measured 5 volts, right? That makes sense? So you understand where we're going from?
Yeah.
So this is a flash converter. Flashing converter is very complicated, but it's extremely fast. And like I said, these are nice to know. But what we need to know is what's an A to D converter going to give us? It's either going to be digital or it's going to be true binary, right? So it's either going to give us a true or false, or it's going to give us a binary number that represents the quantity. And then it would be up to you inside your PLC to do some math to do what? To convert it to what it's supposed to be. Okay, guys, you gotta take a break. 10 minutes. Miss Wilson's trying to come. Yes, ma'am. Wow,
That's pretty good.
No.
I didn't get my phone. I had a fiber optic certification. I had to wait until they do. They just transferred the certification number to it. But what? This certification stuff is pretty good. Okay. Yeah, this one. Yes, sir. It's on your disc. It's on your disc. It's supposed to be all 4 of them.
If you want to get this turned in, you get it out of her. I'll let you record.
Do it again, Mr. Yeah, that's the paper to do. And that's both.
So this would be an example. We bring an analog in to the AD converter, and it's going to output a what? binary number that represents that analog value. But it's not going to be the analog value. Because what it's going to do is it's going to take that analog value and split it into a certain number of counts, right? You know what I'm saying? And it depends on the resolution of the A-to-D converter. So that's where you have to calculate your transfer function to get your PLC or whatever your computer to actually display the true value of what you're receiving. I'll try to do it on that if I can get time. We got a 1100 PLC down here. It's got a 10-bit A-to-D converter on it. It's actually got two analog input. Just give y'all a little feel of what you got. All of the devices that we're using in here are digital. At the sensor class, they call them binary, but I don't like calling them binary because they're digital. So it means they're either going to give us a one, true or false. We try to set up a lab. We do have some encoders that we'll look at and see what we can do with those. We just got those, so we don't have a lab written on them yet. These are what we call absolute encoders. These are digital, but what they do is this guy actually gives us a binary number that represents a position. What it does, it uses optical sensors, which we ain't got so far, which shoots the beam through it. So right there, all the beams would be true. You see what I'm saying? And of course, they say that represents a binary zero. By the way, binary is not that hard. You write down the decimal equivalents of each bit. And it goes 1, 2, 4, 8. What do you think the next one would be equal to? 16, 32, 64, 128, 256, right? 512, 1024, 2048, 4096, 8192, 15,384, 30. But you just take the previous value and do what? Don't tell I've dealt with binary a lot, right? Yeah, I'm not multiplying by 2 in my head. I just know it. Yeah. So here, this would be what we call a 4-bit converter. So a 4-bit, and you can calculate the number of counts or positions you do. This is base 2. You'd say the base, and then you'll raise it to the number of bits. That'd be 2 to the 4th. So this would give us a total of 16 different locations that we could see, including 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And that would be 16, right? Because we started with 0. Everybody okay?
We get 2 from.
Oh, what you do is we can calculate the number of what we call numerical combinations, and they always including 0, by taking what we call the base of the numbering system. So so like, how many combinations can I represent with 2 digits of base 10? We would say 10 raised to 2, and that would give me 100 combinations, which would be 0 through what? 99. Binary is a base 2 numbering system. That's why it goes in 2s. 2. Like this is actually 2 to the 0. This is 2 to the 1st, 2 to the 2nd, 2 to the 3rd. So what we do to calculate the number of combinations on any numbering system, you take the base and you raise it to the number of digits. And that'll give you the number of combinations. So that's what I was doing with 10 bits. I would say 2 raised to the 10th is equal to 1024. But that's including what? 0. So that means I could split it up into 123 combinations, because 0 would be nothing, right? You understand? So that's when I said 65,536, that was 2 raised to the 16, right? So what we mean is this guy right here, but what's nice is that this guy right here gives me a binary number that would represent a position. So each one of these would represent a position. But it's going to have very poor resolution, because I can only see 16 positions, right? You understand? So while my device was in this position right here, it would always say it was at the what position? The 0 position, even though it might do what? It might be moving a little bit, right? Does that make sense? So how would we do that? Well, we'd add another track or add another band. And now they're going to get what? Closer together, and the resolution goes up. So if I add one more bit, then I'd have what? I'd go 2 to the 5th, and that would be 32 positions I could represent in one revolution, right? If I add another bit, that means that's 64 positions I could represent in one revolution of my code. So the more bits we add, or the more tracks we add, the better resolution of the code. But we got to put something that's able to sense every one of those tracks. Does that make sense? What's nice about this though, I don't have to convert it to binary. It's already comes into binary form. So we don't have to run this thing through an A to D converter, analog to digital converter, because it's giving me digital information. So now I can bring it right into my PLC, right? You understand? I could read it and then I can convert that over to whatever it needs by coming up with a transfer function. That makes sense? And what's nice about this guy is you can turn the equipment off, and you don't have to start it from a known position. You can turn the equipment off, and when you turn it back on, it knows exactly where it's at. Right? That makes sense? Are we okay? So this would be an example of an absolute encoder. So we have the light, we have the sensors right here. You can see it's just counting in binary. You have to be really fast. You go all ones, and then when it hits, it rolls back around. See that? This would be a rotary, but we also have what we call a linear absolute encoder. This guy here's only got 4 bands. So this would give a 16 combination. This guy here has 1, 2, 3, 4, 5, 6. So this would be able to give you 64 positions in one revolution. Okay? Make sense? So what's the advantage of this guy? Yeah, well, first of all, if you bring it into a computer, we don't have to do anything to it, right? It's already what? It's already binary. So we could bring this into the inputs of our PLC. Of course, each bit would have to have its own input, right? You understand that? This guy over here's got, this guy's got 9 inputs. So it's got 10 inputs, 0 and 9. So this guy here can handle 10 track code. So we take that whole PLC right there to handle this code. So this would be a linear encoder, and this would actually be the fifth element. This looks like this consists of 1, 2, 3, 4, 5 tracks, 32, probably 32 tracks on there. And notice it gets so small you can't actually walk. You can't even see it. This is counting in binary. So, and we just, what you do, guys, is after a while, some of these patterns you learn, but what does it do? It goes what? 1, 2, 4, 8, 16. So, I mean, if I came over and saw this number right here, if I wanted to find out what the decimal equivalent was, I would go 1, 2, 4, 8, 16, and I would just add the ones that had 1 in it. I'd add 16 plus 12, right? What would it be? Okay? You okay? I don't know why this place got.
You said 8 and 0.
A code is when one thing is used to represent another. The predominant codes used in binary are what we call ASCII. And ASCII gives us the ability to represent other things besides numbers. So now this is not in binary.
code where you have like the little shapes and all that stuff on the street.
Yeah, but it gives us the ability to represent other symbols, represent symbols, right? Like these, y'all know these are symbols that we learned that that is the symbol and we call it the letter A and it has a sound, right? You understand? So this is a symbol. But when I come up here and type this in, this computer has no idea what the letter A is. It represents that with a code. Now the code that we used to, it was ASCII code. The problem with ASCII code was only a 7-bit code, which gave us the ability to represent 128 different characters, symbols. But then we had to do things besides just symbols. We had to send information between the two devices. So like if I was sending information here, what's from here to there? Well, from here to tell it to go down, I had to give it a carriage return. And we can display that symbol right there. So that means I had to have codes that represented not only characters, but also punctuations like spaces, right? And stuff like that. So, Larson, they're using ASCII. They're using ASCII. But they're not doing it in binary, they're doing it in a representation we call hexadecimal. So what's nice about hexadecimal is we can represent 16 binary combinations with one digit. So he set up a sign, 0 to L, he had 16 letters around there, and he would send them the ASCII code. I need to put that part of that movie out when we teach ASCII. So that's the way he communicated.
This was over the guy was stuck on the moon.
No, on Mars.
Yeah.
He was sending ASCII. So hexadecimal is a way that we can represent extremely large binary numbers with very few digits. So the computer uses this a lot. And we're getting a little more in depth than we need to get to. Oops. Where did I put my energy slide at? So we could take a large binary number like this, and then we could come up and split it into groups of 4s. And when you take digital, you'll find out what it is. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then we could write down a number like this, and that would be hexadecimal. And this is a base 16. So a lot of times when the computer's trying to display extremely large binary numbers, it's going to display it in a number system called hexadecimal. So what I'm fixing to show y'all, the code that is being used by the computer is not going to display the binary equivalent. It's going to display, it's going to tell us the hex equivalent. So I can come up here and now, and when I'm drawing this, I can come over here and say insert, and I can come over here and insert a symbol. And then you look at the first few symbols. This is what the computer's doing. So this is the code right here, 0029. But that's not decimal, that's hexadecimal. The actual, that 0029 would actually be, let me go ahead and insert it. But look at all the things I can insert now. But each one of these is represented by a binary code. So my computer has no idea what that character is right there. It sees that code right there, 0258. That's what it saves in its memory as the video memory for buying it, in it. And then my display controller knows when it sees that code, it's got a pattern stored that displays that symbol up there on the screen, which is really, really neat. And that's what you're doing even on your phone when you send an emoji. What are you doing? there's a code, a binary code that goes between the two computers that they send it, and then the other computer gets that code and knows to put these dot patterns on the screen to display a smiley face. Of course, we used to do emojis with regular text, right? Smiley faces and stuff like that. And that's a lot of information. But look, not only do we have English, but also we have available to us several different languages. So with 16 bits, that gives me 65,536 different codes now, which is basically every language that's currently available. So a lot of times, I don't know if if you ever go to an internet site and it says we don't have the codes to support this site, and they're not going to give you all 65,536 codes. You get a standard set of codes in your computer, but you can always add to them. Because every time you load in Microsoft Office, it's got to load in those 65,536 different codes if it's got them there. So that's why Microsoft is not going to give you all of them. It's just going to give you the ones that's most likely for you to use, right? And so we got a lot of neat stuff. So this was the original emojicons right here. But it's a code, 263A, which 263A would be two, 6, 3, 8. And you can see once you learn the trick, you can go between hexadecimal and binary, just not even thinking about it. So this is actually what's stored in my computer for the smiley face. This is stored in the video card. The video has a pattern that represents this code. So when it sees that code in the video memory, what does it do? It sends that pattern. This is nothing but, these guys are nothing but what? Dots. Red, green, blue, and black. The red, green, blue, and black guys, we can do, not necessarily black, we call shades of gray. With shades of gray, we can display any color. And that's all our ICs, right? We got cones and we got rods. I forgot one of them's for color and one of them's for shades of gray. And all we got is cones that see what? Red, green, and blue, right? And then what's the other color? Shades of gray. Well, it's actually shades of gray. So and you combine all 4 of those colors and you can do what? You can make any color. So what they had to do is we got a problem of Unicode. So this is Unicode, by the way. If you looked at the side when I inserted something in here, Unicode. So what they've done is they've expanded the ASCII code. The last 256 characters is the ASCII code. So if I was to get an ASCII code chart and look up the code for the letter A, it would be uppercase that letter A. It would be 41 or 65 decimal. See, there it is right there. 41. That's it. So what they did is they took the ASCII code and just expanded it to make it. Unfortunately, the ASCII code only covered the Latin alphabet. So I don't know if y'all know it, but when the internet first came out, it was ASCII. And everything on the internet was English. So everybody, it's just like the keyboards. It's even the keyboards that on computers were set up on the Latin alphabet. So these other people had to use the internet. They had to do what? They had to learn English, and even to create websites. That was the only option they had. They couldn't do a website in their language. They had to do every website was in English. But when they came out with Unicode, now we can get computers that's got Japanese characters on it, right? You understand? So it's really, really neat what we can do. So the internet now is truly international. When it first came out, guys, it was us. So ASCII is the American Standard Code for information entry. So ASCII was set up over here. Of course, we invented the internet anyway, right? I said, well, it's not we. I had nothing to do with it. The problem we have with the binary code is we have what we call propagation delay. Propagation delay. Somebody did. So what's propagation delay? Basically, that's it. It's how long it takes the output to respond to a change of input. We have propagation delay. Like I touch something hot. I realize it's hot, but before I can get my finger on it, I'm already burned, right? And the story I tell is I had a trunk on my car, and most of y'all probably heard this. I had my keys in my hand, and when I was closing my trunk, my keys slid out of my hand. I watched them things slide down my trunk, and I still did what? Still closed it. No, I still closed the trunk. I couldn't do what? My propagation delay was my brain processed the information before it propagated from my brain down to my hands. I couldn't do what? Stop. So what's happening with the binary numbering system is the number of bits that change. So if the more numbers of bits we change, the more time it takes to propagate through these counters. So notice between 0 and 1, how many bits change? 1, yeah. So from a 1 to a 2, how many change? This one went to a 0. This one went to a 1. So 2 bits had to change. How many changed here? 1. How many changed here? This one was a 1, it went to a 0. This was the 1, it went to 0, so 3 bits had to change. Then I went from a 4 to a 5. How many bits changed? 1. We went from a 5 to a 6. How many bits changed? 2. Then I went from a 2 to here. Went back to a what? 1. And then I went from there to there. How many bits had to change? 4. So you can see the number of bits that had to change, the number of bits that changed between counts varies depending on first of all, which direction you're going, and also what you're counting to. So the propagation delay on the counter, and this was causing some of our counters trying to count extremely high-speed information to miss counts because it didn't have time to do what? To propagate through the thing. So they came up with, but binary is a numbering system. It is weighted, guys. I can come over here and I can convert that to decimal just by going what? 1, 2, 4, 8, 16. I'd add 16 and 8, come up with get what? 24, and I'd be through. So nice. What's nice about binary? It's real easy to convert from binary to decimal because it's a numbering system. But the problem we have with binary, or have with binary, is that it takes to propagate. How long it takes to propagate depends on the count. So what they wanted to do was come up with a code. And what's a code? Something represents something, right? You understand? So they came up with a code called the gray code. Guys, I would have to look this up. I'm sure if you dealt with a gray code, you would understand this. This is not weighted. You can't use the 1, 2, 4, 8, 16 anymore. This is a code. Okay. And how many bits changed from the code from a 0 to the code for a 1? How many bits changed from a code for a 1 to a code for a 2? 1. How many changed from a code for a 2 to a code for a 3? And you notice I can go around here all day long, and what would you find? Yeah, only 1 changed per code. So how many bits changed here? So here, the only thing that's changed right here was this 0. So there was only a 1 bit change. If I go backwards, only a 1 bit change. But it's not a numbering system, guys. It's a code. Right? You understand? It's like the Morse code. The Morse code is not the letter A. It's a what? It's a code that represents the letter A. Right? So this is a code. What did you have to do if you want to do Morse code? What do you have to do? You have to learn Morse code, right? Right? You understand? Or you're going to sit there, look, or you can look at a chart, but you wouldn't get many jobs, right? Because what?
That's what I was in the little.
That's Morse code. It's dots and dashes, and so in each one of them, SOS, dot 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 dot, right? Dot 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 dot. So 3 dots is an S, right? 3 dashes is an O, and 3 dashes. So that was the big things. Save our ship, right? The binary is not a code. The binary is a number system. I can count in binary. I can't count in this. This is not weighted. I cannot go up here and go 1, 2, 4, 8, 16 and come up with the weight of that number. This is not a numbering system. This is a code. This is not a 2 and 0. A 2 in binary is this. This is a 2 in the gray code. A 3 in binary is this. This is a 3 in gray code. A 4 in binary is this. This is 4 in a gray code. Well, what you're doing is you're seeing ones and zeros, and to you they look the same, right? You understand, but they are not the same. And just the 3 numbers that I wrote around, the only ones that are the same is 0 and 1. So 0 and 1 are the same. Now there's an algorithm that you can go, or step-by-step process that you can convert between them, but I don't know. But all we need to know is a gray code. Gray is called a gray code. It's a what? It's a high-speed counting code. Is it weighted? Is it an urban system? No. So if I look at the binary chart, this right here would be all 1. No, it keeps going. But the problem is I'd have to figure it out myself. So I don't really know the code that comes after this. That's a good point. But there is an algorithm and there's a circuit, guys, that in digital we learned something called exclusive orders that will convert this over to binary. No problem. So it's real easy to convert once you learn the trick, but the problem is learning the trick. And I've got a digital book somewhere that gives you the process of converting over the gray. Take a binary number and convert it over to gray. But it's not really important. All we need to do is what is gray code. So binary is a what? It's a weighted numbering system. Gray code is not a numbering system. It is a code.
It's a high-speed code.
It's a high-speed code. So we have if you run into a gray code counter, you know that sucker is running on something that's extremely high speed. That is trying to do what? That it can't keep up with. Now this is the problem that we run into PLC. So originally on a PLC, the counters inside the PLC were software counters. So they were a section of code that might have been that long. Well, the problem is the counter takes time to run through that code. And so what they found out was right off the bat was these PLCs could not keep up with some of the things that counts were trying to keep up with. I don't know if y'all seen some of these can packing plants and stuff like that where they're filling those cans up, and them cans are what? They are flying by. They got these things where they shoot these products over an air gap like potato chips. It's over an air gap. So one conveyor belt is higher than the other. They run the conveyor belts fast enough so it shoots across a gap. There's a camera up there looking at it, making a decision if it matches. These are all computers. If it matches the potato chip they want, if it don't match, they got all these little air vents up there, and they shoot a little spot of air and knock the bad one down inside that trough. And it looks like those potato chips are a solid stream, but now the processing power is so fast, that we can do that kind of stuff now. So what they've done on PLCs is they've gone back to hardware counters, and they call them high-speed counters. So if you ever get into a PLC that says it has a high-speed counter, that is a hardware counter. So one advantage that circuits has over programs is circuits are faster. Programs are slow compared to what? To circuits. So this is an absolute encoder. This is the gray code encoder. This is just an absolute encoder. How many bands does this guy here have? Yeah, this is not a band. This is something else. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 bands. So 9 bands would be 512 positions that it could represent. It might be. I can't remember. Oh, I probably missed it. I missed this or something. 1, 2, 3, 4, 5, 6, 7, 8, 10. You're right. So that'd be 1,024 positions that it could represent in one revolution. But what happens when it makes the one revolution? It starts over. So we have to come up with some type of method to go through multiple revolutions, or we just have to gear it correctly. So no matter what we're measuring, it doesn't make over one revolution. The robots don't use this stuff, even though it appears to, they don't use it. And that's an absolute encoder. This is the actual sensor assembly that's looking at all the bands. This is the one you're going to run into most often. It's called an incremental encoder. What an incremental encoder does, and let's just ignore the index, but it just has a light source. So it has uses light, shoots a light beam over, has a light sensor, which we'll talk about later on. And as it spins, the blade breaks the light. And all it does is just count the number of breaks. Does that make sense? Okay. The problem with this guy is this guy does not give us a count. It gives us a series of pulses. So what we have to do with this guy is we have to have additional circuitry that counts the pulses. But what's nice about this is you're not limited to 360 degrees, right? This thing here never rolls around. What you're limited to is the size of your counters. How many counts can you count? So this is an incremental encoder. This actually came off of an HP printer. So if you take your dot matrix printer and you tear it apart, I guarantee on one side of it there's going to be an incremental encoder. One of them that's on the side is keeping up with where the top of your page is. So that's why it knows. When it feeds the paper in, it trips the sensor so it knows the top, and then from then on it knows how far down it is by this thing doing what? Rotate. We got a printer here somewhere. I need to bring it down. We got the HP printer that one of these things came off of. I think it's in this. I'll see if I can find it. This was the old mouse that we used. Now we use an optical sensor on there that we'll talk a little bit about. So that's why when we pick these things up, I don't know, this might be infrared. Yeah, so it's got this optical sensor right here. But see, this guy here is set up to sense a certain distance. So it's actually looking at impurities on the surface of it. If I just pick it up a hair, it don't what? Don't work anymore. So you can see the encoder, see the little plastic wheels right here? And what would happen is we call this this trackball right here. And when you moved it across the surface, the ball would spin. If you moved it straight, this guy right here would turn, right? You see that? If you moved it horizontal, this guy right here would turn this guy right here. If you moved it at an angle, then what? Both of them would turn. Now we had problems with this is that this guy was making physical contacts with the outside world. He was constantly picking up garbage. This would get up on your little wheels right here, these little guys that turn the wheels, and then they would start slipping. So you'd get your mouse and it wouldn't go vertical anymore. And so you had a little door on the bottom, you could spin it and drop out the trackball. But if you ever lost your trackball, you're screwed, right? And then you would get like a little Brillo pad or something and clean. I use a knife. I take out my pocket knife and just scrape that garbage off there. And after that, it works. Then you take your trackball, which is a metal ball, by the way, so it had weight to it. It needed weight to it. And it had a rubber coating on it. And you'd go and wash that off with just detergent. Clean. So you had to do that. These guys right here, you don't hardly worry about, right? They don't use it. Now what they do to determine direction is they do two things. This is let me bring up my camera. Next break, what we'll do is we'll look at the lab. We'll go over the lab procedures and we'll try to go to the lab. I did find some resistors, by the way. Who's absent? Is Maurice in this one? Somebody else is absent. I need to call Roe. I'm going to use my, here we go. I'll just use the camera that's pointing. So, this is what we call a quadrature incremental encoder. So the sensor was right down here, and you had two of them. One of them was lined up on the bottom track, and one of them was lined up here. And what you can see, if it's turning this direction, then the top one would pulse first, and it would pulse before the bottom. You see what I'm talking about? Yes or no? Now, if I turn it this direction, then the bottom would pulse before the top. So what would happen is the controller would not only know the position, right? You understand? It would also know the direction. So this would run into what we call up-down counters, and depending on the direction, the count would either count what? Up or down. So this is what we call a quadrature encoder. So a quadrature encoder gives us two pulses that are all set by 90 degrees. Which one of them occurs first would tell us what? The direction that we need to count. Because your robot's got to move in what? Two different directions, right? Now the problem with these guys is that if I turn off my equipment and then I turn it back on, your counters are electronic circuits. So what would they do? Well, they'll lose their count. So what does that mean? Well, that means these guys are going to have to be started from a known position. We call it home. And you can tell, you got a printer at your house. When you turn it on, what do? You hear it see, what's it trying to do? Trying to find itself, trying to find its origin or its home position. Once it's found its own position, then these incremental encoders would mean something, right? Y'all understand that? So the paper's no big problem. When your paper feeds, it can find that top, right? And it knows that's what? The top of the page. But that print head that's moving back and forth, it's got to know the exact position of that print head all the time, right? So the problem that we have was these guys, if you're using counters, electronic counters, then if you turn power off of them, what do? They lose the count. So what you have to do is you have to start these things from a what? What we call it an origin point. And what, huh? A known point, but in robots we call it origin. So if we was over in the robot lab, we would show you marks on the robot that we would align on the robot to tell it that if it ever lost its origin. Now what the robot does is it's got a servo motor. And what's a servo motor? Provide feedback. So what it's got on the motor, it's got an incremental encoder, and then it's got its own counters. So the counters are inside the motor, and then it's got a battery. Then the robot's got a battery on it. I guess it's, yeah. And then the battery does what? Keeps power on the counters. So on a robot, it looks like the robot has absolute encoders on it, but it don't. Because what the controller does, it reads the counters. It don't know it's an incremental encoder. So you'll see some people call it an absolute encoder, but technically it's not. It's technically what they call a battery backed up absolute encoder. But it's actually an incremental encoder, but it's got the watt inside there. It's got its own counter. But if those batteries ever run down, and these batteries are inside the robot because they manufacture these robots and I've got to ship it somewhere, right? You understand? So we want it to keep its origin. But if that battery's ever run down and you turn the robot off, then it's going to lose its origin. Which means you got to find the book that tells you how to remaster it or recalibrate it. So, FANUC calls it mastering the robot. You know, if you look at the FANUC, it's got these scribe marks on it. What do? Line up all those scribe marks. You run the mastering program. You line up all the scribe marks and you tell it to remaster. Because if you don't do that, then all the programs won't run anymore. Why? Yeah, I don't know where it's at. It's getting directions, but it don't know where the directions are from. So if you ever get a robot that, most robots will display that, but if you ever get a robot and none of the programs are run, then that's what you probably need to do, check to see if it's lost its master. This robot used limit switches. So it had physical limit switches on it. So what we would do is, when we ran before we ran the program, we'd jog the robot forward and then we'd run a program that would bring it back until it hit the limit switches. As soon as it hit the limit switches, then we knew that was what? 0. So we had to do that every time we ran this robot. So this is the incremental. What they do now, though, most of the time, instead of using the 2 bands, what they do is they just offset the sensor by 90, the actual sensing element by 90 degrees. But most of your absolute encoders now will only have one blade assembly, and they offset the LEDs. Instead of stacking them on top of each other, they offset them by 90. That makes sense. So this is what you see most often. You don't see this much anymore, where they have two tracks, but most of your incremental encoders now only have one. Are we okay? So this is what a quadrilateral encoder would do. Of course, this one's leading, so it would indicate that this would be occurring first. This animation, I don't have the ability to reverse. But incremental encoders can also be linear. But what's nice about a rotary one, the only thing that limits you is your counter. Right? I don't know what the counters are capable on that thing. I know the counters on the 1200 can actually do a double word, which would be 2 to the 32nd bits that it can count. It's big, right? Robots count in nanometers, so you know those counters are used. Are we okay? What's nice about these, though, we can use these for 2 things. Not only can we use it to keep up with the position, we can use it to keep up, know the direction, but the speed of this thing, how fast these pulses are occurring, would actually give us the speed of the actuator also. When we start looking at speed indicators, when we look at speed sensors, guess what we're going to talk about again? We're going to talk about these, right? You understand? So how fast the pulses come would be what? Would be speed. We'll show you how to calculate that speed. And why do y'all need to do that? Because it's on the Siemens Level 1 test. If you take a Siemens Level 1 test, it's going to give you an encoder just like this. It's going to give you a time between the pulses, and it's going to ask you what would be 3,000 RPM. So this is what we do. And we come over here, then we have to go through what? Counters. They could be software counters, but odds are these robots, they move so fast, these are hardware counters. And this is one of the reasons that these incremental encoders, this is one of the main reasons they started adding high-speed counters to because these counters, the software counters couldn't keep up with these motors out there spinning. We got DC motors run 7,200 RPM. And then if you use an encoder that's got 1,000 increments on it, so you can position it more accurately, right? You understand you're talking about some counting. So direction, y'all understand that? Pretty neat, right? Yes, no?
Yeah.
And then, of course, this is what robot uses. Encoders used by industrial robots such as FANUC have taken different approaches to the terminology. These manufacturers use absolute as their terminology for incremental encoders that have what inside there? It has the battery. Well, it has the counter. The counters are part of the encoder. So if we have an opportunity to go back over there, normally what we try to do is, one of the last things we do is we try to go over there to the line, find all these sensors on the line. Let y'all actually find them. We'll show y'all the increment encoders on one of the big fans that we take apart. But I should rephrase that. Not only do we have the increment encoders, but it's also got what? With counters and battery backup. So every one of these robots has got a panel you pull off and you replace those batteries. You need to do it. Rule of thumb is every year you replace the batteries. Because if it does go offline and you lose your origin, then the robot's going to be offline until somebody comes in and does what? Remaster. In fact, we can show y'all the preventive maintenance on the FANUC that was donated by Mercedes. Inside the door, they got the preventive maintenance on when they changed the batteries out in